Welcome to our cosmic journey, explorers of the universe. Today, we're diving deep into one of the most profound and mind-bending concepts in science, the Big Bang Theory. How did our universe begin? What sparked the creation of everything we see, from the stars twinkling in the night sky to the galaxies swirling billions of light-years away? Buckle up, because we're about to unravel the origin of the universe in a way that will leave you awestruck and hungry for more. Let's embark on this epic adventure together. To start, imagine a time before time, a moment before space, light, or matter even existed. It's hard to wrap your head around, right? The Big Bang Theory is our best scientific explanation for how it all began. About 13.8 billion years ago, the universe as we know it burst into existence from an unimaginably hot, dense point. This wasn't an explosion like a firework blasting into the sky. No, it was an expansion, a rapid stretching of space itself, carrying energy, matter, and the seeds of everything we know today. But how do we know this happened? What evidence supports this wild idea? And what does it mean for our place in the cosmos? Stick with me, and we'll explore every fascinating detail. Let's begin with the basics. The term Big Bang was actually coined by a British astronomer named Fred Hoyle in 1949, and here's the twist: he didn't even believe in it. Hoyle was a proponent of a rival idea called the steady-state theory, which suggested the universe had no beginning and was eternally expanding with new matter forming to fill the gaps. But the Big Bang Theory, first proposed by a Belgian priest and physicist named Georges Lemaitre in the 1920s, gained traction as evidence piled up. Lemaitre called it the hypothesis of the primeval atom, imagining a single, superdense point that expanded to form the universe. It's a bold idea, but science thrives on evidence, not just imagination. So, what convinced scientists that this cosmic birth story holds water? One of the first clues came from the stars, well, actually, from the galaxies. In the 1920s, American astronomer Edwin Hubble made a groundbreaking discovery. Using powerful telescopes, he observed that light from distant galaxies was shifting toward the red end of the spectrum. This phenomenon, called redshift, happens because light waves stretch as objects move away from us, much like the sound of a siren stretches and deepens as an ambulance speeds away. Hubble's measurements showed that nearly all galaxies were racing away from each other, and the farther they were, the faster they moved. This wasn't just a random motion, it suggested the universe itself was expanding. Now, here's where your curiosity should perk up: if the universe is expanding today, what happens if we rewind the clock? Run time backward, and everything. Galaxies, stars, matter, converges to a single, incredibly dense point. That's the Big Bang in a nutshell. But redshift alone wasn't enough to seal the deal. Let's travel to the 1960s for the next big piece of evidence, one that's truly cosmic in scope. Two radio astronomers, Arno Penzias and Robert Wilson, were tinkering with a giant antenna in New Jersey, trying to detect faint radio signals. Instead, they picked up a mysterious hiss, a low-level noise coming from every direction in the sky. They checked for interference, pigeon droppings on the antenna, equipment glitches, but the signal persisted. What they'd stumbled upon was the cosmic microwave background, or CMB for short. This faint glow is the afterglow of the Big Bang, a snapshot of the oldest light in the universe, dating back to about 380,000 years after the initial expansion began. Why 380,000 years? Well, in the earliest moments, the universe was a scorching, dense soup of particles and energy, too hot for light to travel freely. As it expanded and cooled, protons and electrons combined to form neutral atoms, and light broke free, filling the universe with a glow we can still detect today. Penzias and Wilson's discovery earned them a Nobel Prize, and it's one of the strongest pillars supporting the Big Bang theory. Doesn't that make you wonder what other echoes of the universe's birth are out there, waiting to be found? Now, let's dive deeper into those wild early moments. Picture the universe a fraction of a second after the Big Bang. We're talking less than a trillionth of a second here. At this stage, the universe was unimaginably hot, billions of degrees, and packed into a space smaller than an atom. Time, space, matter, and energy were all tangled together in a state we can barely comprehend. Physicists call this the Planck epoch, named after Max Planck, the pioneer of quantum theory. During this fleeting instant, the four fundamental forces we know today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were likely unified into a single superforce. Then, in a blink, the universe underwent a mind-blowing phase called inflation. Proposed by physicist Alan Guth in 1980, cosmic inflation suggests the universe expanded faster than the speed of light, growing from smaller than a proton to the size of a grapefruit in less than a trillionth of a second. Why did this happen? Scientists think a mysterious field, driven by a hypothetical particle called the inflaton, powered this rapid stretch, smoothing out the universe and setting the stage for everything to come. It's wild, right? How could something so tiny become so vast so quickly? As the universe expanded, it cooled, and strange things started to happen. Within the first second, the fundamental forces began to separate. Quarks and gluons, the building blocks of matter, swirled in a hot, chaotic plasma. By about 3 minutes in, the universe had cooled enough, down to a mere billion degrees, for protons and neutrons to stick together, forming the nuclei of the lightest elements, hydrogen, helium, and a sprinkle of lithium. This process, called Big Bang nucleosynthesis, is a cornerstone of the theory because we can measure the amounts of these elements in the universe today. Guess what? The predictions match. About 73.5% of the universe's mass is hydrogen, 24% is helium, and trace amounts are lithium, just as the Big Bang model predicts. It's like finding a cosmic recipe book and confirming the ingredients match the dish. But what about the stars and galaxies? They didn't form right away. For hundreds of thousands of years, the universe was a dark, foggy place, filled with a plasma of charged particles and light bouncing around. Then, around 380,000 years after the Big Bang, it cooled to about 3000 Kelvin. Electrons finally paired up with nuclei to form neutral atoms, and light could travel freely. This is the era of the cosmic microwave background we talked about earlier. Over millions of years, gravity got to work. Tiny ripples in the density of matter, left over from the inflationary period, began to clump together. These clumps grew denser, collapsing under their own gravity to ignite the first stars and galaxies. By about 1 billion years after the Big Bang, the universe was lighting up with brilliant beacons of light, and the cosmic web, clusters, walls, and filaments of galaxies, began to take shape. Isn't it amazing to think that the seeds of every galaxy, including our Milky Way, were planted in those first fleeting moments. Let's pause for a second and marvel at the cosmic microwave background again, because it's not just a glow, it's a treasure map. Scientists have used satellites like COBE, WMAP, and the Planck spacecraft to map this ancient light in exquisite detail. What they found are tiny temperature fluctuations, variations of just a few millionths of a degree. These ripples are the fingerprints of the Big Bang, showing us the slight differences in density that eventually grew into stars, galaxies, and clusters. The patterns match the predictions of the Big Bang theory and the inflation model with stunning precision. It's like looking at a baby picture of the universe and seeing the blueprint for everything we know today. Doesn't that make you curious about what else this cosmic snapshot can tell us? Now, you might be wondering, what was before the Big Bang? This is where things get tricky, and incredibly intriguing. The truth is, our current understanding of physics breaks down at the moment of the Big Bang. Time and space as we know them began with that expansion, so asking, what came before, might not even make sense. Some scientists speculate about a multiverse, a collection of universes where ours is just one bubble among many. Others explore quantum gravity theories, like string theory or loop quantum gravity, to probe what might have existed at or before that initial moment. But here's the honest truth, we don't know yet. And that's part of the excitement. The Big Bang theory doesn't claim to have all the answers, it's a framework, a starting point that invites us to keep asking questions and exploring the unknown. Let's shift gears and talk about the universe's composition, because the Big Bang theory also helps us understand what the cosmos is made of. After decades of study, scientists have pieced together a cosmic inventory. Ordinary matter, you, me, stars, planets, makes up just about 5% of the universe's total energy. The rest? About 27% is dark matter, a mysterious substance that doesn't emit or absorb light but exerts gravity, shaping galaxies and holding them together. Then there's dark energy, a bizarre force driving the universe's expansion to speed up, making up roughly 68%. The Big Bang theory doesn't directly explain dark matter or dark energy, but it sets the stage for their discovery. The ratios of hydrogen and helium from nucleosynthesis, the expansion rate from Hubble's observations, and the CMB all fit into a model called the Lambda Cold Dark Matter Model, or LCDM. It's the standard picture of cosmology, and it's rooted in the Big Bang. But dark energy and dark matter remain puzzles, cosmic mysteries that keep scientists up at night and fuel our curiosity. Speaking of expansion, let's explore where the universe is headed. Hubble's discovery showed the universe is stretching, but in the 1990s, astronomers found something shocking. By studying distant supernovae, exploding stars that act as cosmic distance markers, they discovered the expansion isn't slowing down, it's speeding up. This acceleration, driven by dark energy, suggests a future where galaxies drift farther apart, stars burn out, and the universe grows colder and darker over trillions of years. Some call this the Big Freeze, a quiet, chilly end. But other possibilities exist. If dark energy behaves differently, we might face a Big Rip, where the universe tears itself apart. Or perhaps expansion slows and reverses, leading to a Big Crunch, a collapse back to a dense state. The Big Bang theory doesn't dictate the ending, but it gives us the tools to explore these wild scenarios. What do you think the fate of our universe will be? Let's zoom in on how the Big Bang Theory has evolved. It's not a static idea. It's a living, breathing framework shaped by decades of research. In the early 20th century, Einstein's theory of general relativity laid the groundwork. His equations described a dynamic universe, one that could expand or contract, and the Big Bang fits perfectly within that framework. Lemaitre's primeval atom idea, Hubble's redshift, the CMB discovery, and the theory of inflation all built on this foundation. Today, physicists use particle accelerators like the Large Hadron Collider to recreate conditions similar to the early universe, studying how particles and forces behaved. Telescopes like the James Webb Space Telescope peer back in time, capturing light from the earliest galaxies. Each discovery refines our understanding, and sometimes challenges it. For example, recent measurements of the universe's expansion rate, called the Hubble constant, show slight discrepancies between different methods. Is this a hint of new physics, or a measurement glitch? The Big Bang Theory invites us to keep digging, to stay curious. Now, let's address some common misconceptions. The Big Bang wasn't an explosion into space, it was the expansion of space itself. There was no outside for it to explode into, because space, time, and everything else began with the Big Bang. Another myth, the theory claims to explain everything. Not true. It describes the universe's evolution from a fraction of a second onward, but the exact cause or the state at time zero remains a mystery. And no, the Big Bang doesn't conflict with all religious or philosophical views. Some see it as a scientific description of a creation process, while others debate its implications. Science and belief can coexist, and the Big Bang Theory is a tool to understand the how, not necessarily the why. Doesn't that open up a universe of questions for you to ponder? Let's take a moment to reflect on the human side of this story. The Big Bang Theory isn't just equations and telescopes. It's a testament to our curiosity, our drive to understand our origins. From ancient myths of cosmic eggs to modern supercomputers simulating the early universe, humans have always looked to the sky and wondered, where did we come from? The Big Bang Theory is our best answer so far, built on centuries of observation, math, and imagination. It's not perfect, and it's not complete. Scientists still wrestle with questions about inflation, the nature of dark matter, and what quantum gravity might reveal about the universe's birth. But that's the beauty of science, it's a journey, not a destination. Every question we answer sparks 10 more, and each discovery brings us closer to understanding our cosmic story. So, what does the Big Bang mean for you and me? Look up at the night sky. Every star, every galaxy, every speck of light began in that hot, dense moment 13.8 billion years ago. The atoms in your body, carbon, oxygen, nitrogen, were forged in the hearts of ancient stars, but the hydrogen in your water, your cells, traces back to the Big Bang itself. You are a piece of the universe, a living echo of its origin. Isn't that mind-blowing? The Big Bang Theory connects us to the cosmos in a way that's both humbling and thrilling. It tells us the universe had a beginning, and it's still unfolding, carrying us along for the ride. As we wrap up, let's gaze forward. The Big Bang Theory has transformed our view of the universe, but the adventure is far from over. New telescopes, like the Vera C. Rubin Observatory, will map billions of galaxies, probing the expansion and dark energy. Experiments in particle physics will hunt for clues about the early universe. And maybe, just maybe, we'll crack the mysteries of what came before, or if before even applies. The Big Bang Theory is a foundation, a springboard for discovery, and it invites you to join the quest. What questions does it spark in your mind? How did this vast, beautiful universe come to be, and where is it going? I hope this journey has ignited your curiosity, because the cosmos is full of wonders waiting for us to explore. Thank you for joining me on this epic dive into the Big Bang Theory, the story of our universe's origin. If you're as fascinated as I am, hit that like button, subscribe, and ring the bell for more cosmic adventures. Drop your thoughts in the comments. What blows your mind about the Big Bang? What do you want to explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Explorers.